Hey everybody, welcome back. We are still talking about the bones. So this time we're going to talk about how bones grow and remodel. We looked at a couple of ways that they grow, but we're going to look at how they kind of grow after they're initially formed. So that's kind of the difference with this one. Okay. All right, so the growth in the length of a long bone occurs at the epiphyseal plate. And that's kind of where we left off when we were talking about epiphyseal fusion. And so it just like this is the only place that it really has to kind of move. So basically, if we have these, terrible arrow, there's an arrow, right? Here's like an epiphyseal line. And then we have this one kind of adding bone and adding bone. They can keep adding and pushing towards each other in a way that allows them to really kind of extend until we have absolute fusion, right? So that's how that operates. The ossification zone is the part where all that new bone is forming, right? And so it's more like deep to the bony structures, if you will. The calcification zone is where we're dropping off cartilage, or I'm sorry, we're dropping off calcium, right? And we're calcifying that particular area, and that kind of kills off the cartilaginous cells. Remember how cartilage cells look right here. Usually they're in these little dyads and they look, nice and floofy and pudgy and smooshy. Um, so, right. So hypertrophic zone. So hyper means, uh, means, more than or accelerated. And then trophic means eating, right? So that means that we have all of these older cartilaginous cells, they start to get like really big, right? Because the idea is what they're consuming more, and so they're becoming like physically larger. Okay. And let's kind of go back over here. So here we have the bone tissue, osseous tissue, kind of starting to cover up on the cartilage, and it's going over, and as you can see, we are down to much smaller isolated nuclei as we're calcifying, which is very different from these like nice thick juicy cartilaginous cells. This also gives way for more vascularization to move through the bone as well, because remember, bone is highly vascularized, whereas cartilage is like a not so vascularized tissue, so it's like less easily able to repair itself, heal, and all of that good stuff. Here's an osteoblast, right? Here's one of many that are depositing that new bone, and here are some of the cartilaginous matrix, right, which is really dark purple over here. It's just where you don't see the cells, but they're all swimming in that purple lake. That is when we start calcifying the matrix, right? Okay. Finally, the proliferation zone is referring specifically to the cells of the cartilage, and this is the cells that are undergoing mitosis. See, they're smaller because they're just newly divided and dividing, and that's again where we see the hypertrophic zone. They're larger, they're better, I'm sorry, more developed. So, right, so that's the growing length of an epiphyseal plate. Um, Now let's talk a little bit more about bone growth and bone remodeling. So, what ends up happening too is I want you to first notice here is the shape of the bone on this side. So, bone does this thing where it resorbs, right? Resorbs. And so bone starts to be resorbed and reused. So we'll use that calcium to maybe extend in different directions and to rebuild some of that matrix. The bone is going to be replacing the cartilage. The cartilage will stay here at the articular cartilage, right? Because it's articulating or touching or moving with the other bones in that joint. Until there's arthritis and there's less of that. Also, here's that epiphyseal plate or epiphyseal line right here. What it is also referring to is this idea where here's the epiphyseal plate, right? So when you have two forces opposing each other, right, essentially, and growing towards each other, we refer to this as like an appositional growth, right? So that's what that is. And we're also moving like inwards towards all of the bone and kind of pushing upwards. So it's this like pushing motion, if that makes sense, right? So here it goes. All right. Resorption is a function of the osteoclasts. So osteoclasts are different. Osteoblasts are the ones that are building bone and mitotically active, making babies. Osteocytes, they just aren't making any cell babies, but they're maintaining the, calcium matrix, the bone matrix itself. But osteoclasts very specifically go in and they start tearing apart the bone, right? They're degrading it and they're freeing up that calcium, right? To go back into the bloodstream to be used by the brain, by the heart, by the muscles, and all of that stuff. Just because there might not be enough bioavailable calcium. This is one of the ways we can get things like osteoporosis and all of that. They dig depressions, grooves, holes in the bone as they break down the bony matrix. Part of how they operate is they have lysosomes, right? Lyso meaning to break apart or to split. And they use these enzymes that are also able to basically acidify the area, and it helps digest that matrix. All right, and so it's a balance, and one of the really important parts of that balance is the thyroid gland. Oh my goodness, so important. This little gland in your neck, right here's your larynx, right here. Here's your voice box and your trachea and all of that coming right off of it. The thyroid glands, parathyroid glands actually, are these teeny little like nodules embedded into it, and they release parathyroid hormone. Parathyroid hormone, when there's too much of it, cause osteoclasts to break down that bone, right, and eat it up. And it means that there's not enough calcium, or there's a higher release of calcium in the blood. And that's ideally, if you needed that calcium, that's how it would be regulated. And so what ends up happening is those thyroid, parathyroid glands actually, they sense that calcium level whenever there's a falling calcium level in the body, that stimulates them to start releasing PTH, that parathyroid hormone, again, which causes osteoclast. But if calcium levels rise, it can help suppress, right, their ability to tear apart that bone, causing osteoporosis, weakened bones, resorbed bones. And so that's why it's important to have bioavailable calcium in your diet. Bioavailable calcium, right? So calcium needs to be eaten with or ingested with vitamin D, absolutely essential. It's a catalyst for it to be able to uptake and integrate it into the body, into the bones, and use it. Otherwise, it kind of can just flow right back out. Maybe not entirely, but in larger amounts. So vitamin D is essential for that. Also, we think of only cow's milk and cheese as a exclusive source of calcium because it is calcium rich, but also calcium citrates that we can find in things like spinach, green leafy vegetables, arugulas, it's broccolis, all of that good stuff. Those are other wonderful ways to bump up that calcium, as well as just good old-fashioned supplements, as long as they are calibrated and calculated correctly. Keep an eye on that calcium. It's a blood test. It's easy peasy. Okay. All right. So control to mechanical stress. So if you will have denser bones if you have more resistance or stress on them, because it physically forces them to become more tightened, closer together, right? Less, all of those little cracks and pores that are created through osteoporosis now kind of have to crunch down on each other and like repair in that way. So Wolff's law is a law referring to physics, and in this case biomechanics, that states that the bones are going to grow or remodel and reshape themselves in response to the demands placed on them, right? So if you are constantly working out one arm with lots of resistance and heavy stuff, and the other arm is just sitting there, I don't know, holding a remote control or a book or whatever, one arm is going to have, the arm that's doing all of the resistance and physical lifting and weights is going to be the one that has a denser bone, right? Because the muscles are pulling down on it constantly, right? Also pulling anything out of shape, which is important why we are going to reset broken bone so that it doesn't fuse at odd angles or incorrectly. So that's important. That stress needs to be direct and on the center. And in humans, we have these very, very, very straight linear bones compared to a lot of other animals. They might have like more thick ridging and bends in them. So right? We are definitely upright bipedalists, and so we have that direct force with gravity, that up and down. Okay. And here's a great example. So this is the femur. Here's the head of the femur right here. And so the body weight load goes down. So we have stress here, but a lot of that weight is again up and down because we are bipedal and upright, So like another animal who might be more of a quadruped would have more of an angle to their body weight, but we don't. We are definitely an up and down straight. So the tension is going to be moving apart, but the compression points are going to be moving closer together until we reach a point of zero stress between the bones. Okay, I think that's really just it. Okay, so I hope that was helpful. And yeah, okay. Well, I hope all of you are out there somewhere out there having a wonderful day. Bye bye.